Run. Now we're recording. So this file and everything in it in this chapter is all in a zipped file that you just download into your own computer. All right. And you'll run it, and there should be a sample situation that comes out. Right. And it'll have, what I've done though is set the amplitude of this to 0. So that once after you run it, you run the Python code, and it will tell you the RMS or the theta, the noise scale factor, the full width half maximum. And now, yeah, this is actually wrong because I'm not forcing it in this run. And that this plot here that pops out, and just let me do it again. All right, is a curve fit of the blue data. And so that blue data is this right here. And so it creates a Lorentzian fit and then finds this point, and that F is the full width half maximum. Now it also spits out the RMS signal. All right. In this plot though, it's 1 over. And so what you would do, all right, is that each team is going to have this worksheet, and I'm going to share it with you. And so in this case, I just happen to know the scale factor is 1, and the theta was like 0.24, right? And the full half maximum was like 63, right? Now, we actually plot 1 over theta. All right, so we just have to calculate that. Okay, and so this is 4-point change, right? And so it's not really on this plot. It's off to the side, all right? But the full width, yeah. So out here at 4, right, the full width half maximum would be 63. Now, as we're going, what I want to do is just show you how long things take, right? So that's at a scale factor of 1. Now I want to do a scale factor of 1.1. And you'll see that it can take some time. So this is where the teams are going to be great, is because you're going to want to go all the way up, maybe not by tenths, but you're going to want to go up to 4.5. And you can try 4. Actually, you can go increments of 4 in quarter increments, which is a lot of data, right? But when you split it up amongst 3 people, right, whatever team 1 is, right, you got to put that in there, write everything, and make sure you don't screw up the other people's data either, all right? Just to tell you. So you can see, even while that's going on, it's taking some time, all right? So this 1 over theta and the full width half maximum is this plot, all right? It's just not, there's different conditions, so it's just not going to line up, all right? Now, let's see. While that's working, let's just see if I moved everything to this desk here. I don't know if a wire popped out. All right. But in the video, I show you how to enable the power supplies. But the thing is I've also saved some preferences that if you go into where that directory is, there should be something called Scopy SR, and you can read that in, right? So you enable that, and then it's set up for the noise measurement. But what you can do is channel 1, right? It should have this triangle wave set up. And then channel 2, you want to set that to a constant, press run. Then go to the oscilloscope and press run. And you should see the classic Schmidt trigger. Yes, it's still working from yesterday, right? And this today, everything is working really well for me because this is almost exactly 1 volt. Sometimes I get junk, and maybe it has to do with how I'm doing things, how I built it that day. Then come back, channel 1, set to buffer. Now you're going to have to load the file in wherever you put it, okay? And it's noise.wave. And there's the noise. And here's the thing. This is why you want to keep track of the scale factor, because amplitude of 1 is actually a scale factor of 1. And then you can do different scale factors, all right? And then for channel 2, you can try, there's a part where you do a constant, and then there's the waveform. And let's see if this is done. Looks done. Okay. Now we really don't have a sine function in there. Okay. So the signal to noise ratio doesn't make sense, and this frequency doesn't really make sense. All right. However, we got 2.2.2. Like 0.26, and what was it? I think it was 78. Or 79. Can round it up. Now, yeah, actually, these will all be the same for every group. All right. Now, over here, right, so each group is going to pick a different full width Kramer's rate frequency. All right. So these are this is the Kramer's rate and 1 over the Kramer's time. And so everyone's going to pick a different frequency, each group, right? And I'll tell you what each team will get. All right. And then you'll go back to LT Spice and set the scale factor to make that happen, right? And what you'll do is go back to scale. Right? Oops. That's supposed to be 0.2. So then you'll come back here, right? And you're going to, each team member will have a different amplitude, and then they're going to sweep the noise RMS by changing the scale factor each time, and then measuring signal to noise ratio. So I have to run that again. So now, while that's doing that, we can run the spectrum analyzer. And it takes a little bit of time for it to calculate. All right. And if the sweep isn't exactly right down here, click the sweep and just go from 1 to 5 and then scale it in RMS from like 0 to 4. You might have different values. But now I want to measure the peak of that marker, right? Now I happen to know that it should be at 63 hertz, right? That's the frequency that the group is going to do. And so then it's going to put, eventually, oh, that's because it's kilohertz. My bad. Okay. So there's the marker. And it can be a little faint. Maybe in Zoom it's hard to see. But you have 3.86. All right. So over here is it's going to be measured. Right, the forcing frequency is 63 in my example. Now I can measure the RMS in Scopy. I forgot to mention that in another video. All right, and I'm going to turn the XY off just so it's a little bit easier to see. And then you need to kind of scale out a bit. All right, and now it's actually measuring RMS, and it's 0.27 volts. Okay, so this is what I measured from Scopy, and yeah, you're going to have to adjust time scales and things like that. Then the V peak of the input was 0.2. No. Or let's call it V peak to peak, was 0.4. And that, again, that's from Scopy, right? This is peak to peak, not the amplitude as it is from LT Spice. So that's where that number comes from. And then we can call that VP, stochastic resonance, VP, no, stochastic resonance, and that was 3.76, I think. Right. Then now I want to measure it without this to get the signal to noise ratio. So I click on constant, it's 0, go back to the spectrum analyzer, click run, let it calculate for a bit. We're still at 62 hertz, and now it's 0.56. So that's without the noise, and that's without the sine wave. 0.56. And so then our signal to noise ratio is the ratio. 6.7. All right. And so each team is going to have the frequency will remain constant, but you're going to change theta, right? And then one team member will each tackle a different V peak to peak, all right? And it's better to show it here, all right? So in this plot, right, it's at 180 hertz. Everyone's going to have a different frequency. They're changing the RMS noise, which is effectively changing the scale factor. But one team member will do a smaller V peak to peak. One will do a V peak to peak in the middle, and one will do one here. I'll give you these values, all right? But to show you how it would work, right? Let's do a V peak to peak in Scopy of 0.1. So I go back to the signal generator. I'm on channel 2 waveform. So V peak to peak, 1 millivolt peak to peak. We go back to the signal generator. I mean, spectrum analyzer. All right. And it's giving me 1.1. Okay. Now the thing is without the noise, it's still the same. So that's my signal to noise ratio, right? And then what I would do is change theta throughout the range here, right? And I would create this plot, right? And somebody would create that plot. And so each team member will create one of those, all right? Now, it looks like there's 18 active people, all right? Or fewer. It's hard to say. Not everybody can make it to these talks. But basically, if you know, it looks like we'll probably have 5 or 6 teams, all right? And those are the measurements that you're going to do. And I'll have to update the lab manual so that tomorrow, really, you can just work on it, split up the work, and then do the plots. All right. And then we need to get ready for our oral presentations, and I will give you a very simplified format just to kind of present your results. But here's the thing, right? You're all going to be doing different frequencies and kind of different curves. But if we have 5 teams, if we have 5 teams, we're going to have 5 of these plots at different frequencies, right? These are just sample plots, right? This plot is all the same. We all have, that'll all be the same, right? And this is just a sample plot, but that's a lot of data that would be kind of hard to do on my own. And so by doing these measurements, right, you are really contributing in an authentic way to the research program. And now then the next step would be like next week, right? If we weren't going back to school and you were going to do research with me, right, actually I want to go back to the oscilloscope and see something. All right. How does the width of the hysteresis region affect things, right? So that's a research question that now you were pretty much able to study on your own. Another research question, right, is now changing these two resistors changes the width of the hysteresis region, right? Now, this noise source has a particular um, actually, I'm going to turn that off. And okay, this is the noise where you can see it's rolling off a little past 1 kilohertz. Well, I designed it that way to match the paper, but we can manipulate the frequency of this so that it gets pushed out. And it's actually really easy because if I go here, go to waveform, no, buffer, right? I can speed it up by changing the sampling rate. All right, so see how it's coming down around 10? Well, how does that change its response? What's the fastest signal that it can detect? What's the slowest signal to detect? And so if we had, let's say, 5 teams, right, we could answer 5 different research questions and really advance the knowledge of what's going on. So that's we might have forgotten or might not have seemed it, but I was really trying to prepare you to conduct research in this area and research in general. Where all right, here's how to do a circuit, here's how to plot things in Python, and maybe you don't follow everything, right? But you know that there's such a thing as curve fitting and how to share data. And then there's another thing I wanted to show you about working in teams is what I want you to do. Right, is you create a project task list, like you have the final presentation, who's in charge of it overall, right? But then you have sections, right? Who's going to do that? When is it going to be due? Where's the link? What's the status? All right. Now, yeah, there's in here could be I'm in charge of this frequency and this measurements. I'm in charge of the LT spice part. I'm in charge of the measurement part, right? So that everybody knows what they're supposed to do and when. Now, yeah, we only really have a day, but this thing could be super important. All right, but that's pretty much it. The lab manual has a video that I think goes in more detail, and there's some figures to help you get going, but you should be able to start, at least repeat what I showed today so that tomorrow you can start with your own frequencies and amplitudes. All right. And I just, in that Python, right, if it says file not found, you have to kind of copy the path so that it can find it. All right. Any questions? The WAV files they're already done for you. And I don't think you used them in chapter 3. But if you were on your computer and it was a Windows machine, this is the zip file, and inside the zip file is everything you need. Okay, so in order to find the path, it's it's shift right click. Somewhere it'll say, it should say, or no, is it control? Right click. So copy as path. All right, and then you can paste it where you need to go. Which I think I described that in the manual, so you don't have to remember that right this second. But it's probably best to, like, if you read the manual, it'll say, watch this video first, right? And that'll kind of give you an overview of everything. Then you could rewatch this video. But really, this is a prelude to tomorrow's exercises where you actually start doing your authentic research tasks. All right, I'm gonna stop recording, and everybody can break out, and